Okay, good morning. This is our lecture number 8, and we have been discussing about conservation of momentum in the previous lecture. So, now we'll discuss one of its other variant. So, the way we have described continuity equation for one dimensional multiphase flow, similarly, I have defined over here the one dimensional momentum equation for nth phase. So in case of one dimensional equation, again we will be doing area averaging. So over here the time term remains the same, rho n alpha n into un, whereas in the advective term, now instead of having the variation over the area, we will be having actually uniform value at the entire cross section. So that's why I am using this 1 by a over here, and inside I am using actually 1a in multiplication. So a rho n alpha n. Now there are two differences. One difference you already know from continuity equation, because we are dealing only for the variation in one direction. That's why this subscript with x is actually dropped. Okay, because we are only referring to the single direction. Second variation is, earlier if you recall, in the momentum equation we were having one term as uni, other term as un k, where u and I were referring to normal velocity in phase I, okay, and u and k was referring to velocity of nth phase in kth direction, okay. But when we are talking about the one dimensional flow, for one dimensional flow area averaged thing, my variation will be only in this side, so this will be my kth direction, and as we are considering the momentum exchange only in kth side, so I will be equal to k. So that's why these two velocities u and I and u and k will be becoming same, and as we are referring to only a unique direction, so we are not using any index as subscript. Okay, so we are getting this as u n square. Then in the right hand side, del p by del x plus other term was in terms of the del by del x of the stress. Okay, when I am having area averaged quantity, then for area averaged quantity along the length of the pipe, I can define some wall shear stress. Okay, is this point clear? And this wall shear stress will be acting on the surface area. So wall shear stress in terms of force, if I have to calculate force from wall shear stress, then I can write it perimeter into length. Is this point clear? What is surface area? For example, if you consider a cylindrical conduit, then for cylinder surface area will be 2 pi r, which is perimeter into L. So in general, because I can have conduit of any shape, so in general I can write surface area to be perimeter into length. And as we are writing these quantities on per unit area basis, so divided by I will be writing A, where this A is nothing but my cross-sectional area. Okay, is this point clear? Because we are writing equation on area average basis, so this is my cross-sectional area. And now, because the stresses, all the velocity gradients are existing only in the single direction, so that's why instead of defining the complete stress tensor, only one gradient in this direction will be giving me the wall shear. So I am directly using it. Okay. So now if I do divided by this area, sorry, when we define this equation, we write it on per unit volume basis. Okay, so divided by area, and in order to make it volume, it will be cross sectional area into length. Is this point clear? Because ultimately, whenever we are writing this momentum equation, this entire equation is on area averaged equation, but on per unit volume basis. Is this point clear? So, in order to make volume in the denominator, this cross-sectional area has to be multiplied with length. So, length will cancel out, and inside I will get perimeter into tau w divided by A. So, please clearly note the difference. For pressure I am using symbol small p, and capital P over here is for perimeter. Okay. Now, we know that this is the surface force which is acting across the boundaries of the control volume. Okay, so this surface force will be only applicable for continuous phase. That's why with this surface force I have used over here Kronecker delta operator. Okay, and we know already from the previous lecture when this delta n will be 1 only for n is equal to c. Okay, because across the boundary, basically this wall shear stress and pressure, these are acting at the boundary, and at the boundary of control volume only we have made the assumption that only continuous phase is actually in the touch. Okay. Then for body force, I will be having alpha n rho n into gx. Okay, and then for this term is, can you tell me what is this? Interaction force. Okay, and this interaction force has also to be acting in the single direction, and direction over here we have taken as x, so that's why I am writing over here x. So this is my area averaged individual phase momentum equation. Okay, what is this? This is, if I write this equation, if I extend this equation for individual phases and take their sum, then I will be getting summation over the n, rho n alpha n into un plus 1 by a del x of a will be coming outside because summation is happening over the individual phases. So rho n alpha n un square equal to, and when I will be doing the summation, that summation is also including the continuous phase. Okay, so this term will be only applicable for continuous phase, so one time this will be coming here, and all the summation of interaction terms will be becoming equal to 0, interaction forces will be 0, and from this term I will be getting summation of rho n alpha n into gx, and summation of rho n alpha n, because gx is a constant quantity, so rho n into alpha n will become rho mixture density. Okay, so I can call this equation as nothing but combined phase momentum equation. Is this one clear? Now, as we are referring to single direction, and if I now make one assumption that un is equal to u, what it means? All the phases are moving at the same velocity. Okay, so there is no drift between the phases present. In that case, this un can come out of the summation. Okay, because un is now a constant value u, so un can come out of the summation, and this summation of rho n and alpha n will be becoming mixture density rho. So del by del t rho u plus 1 by a del x of, here also un square will become u square, so a rho u square minus del p, and right hand side is as it is. So what will be this? This was area averaged combined phase momentum equation. Okay, this will be area averaged mixture momentum equation. And of course, this mixture is present in such a way so that there is no drift between the phases. Okay, all are clear with this point? Now let's talk about the equation of momentum in terms of number density. Okay, so we have seen earlier the momentum equation in terms of number density. So let's consider that an individual particle is having volume Vd. Okay, so I am having some individual dispersed phase particle which is having volume equal to Vd. Okay. So for this particle, what will be total rate of change of momentum? Total rate of change of momentum will be d by dt of dispersed phase into of density of the dispersed phase, volume of that particular dispersed phase particle into velocity of the dispersed phase particle. And of course, this particle can have velocity randomly in any direction. So the direction along which we are trying to write its momentum equation, I have to take component of the velocity in that direction. So that's why with velocity I am using subscript k, which is representing the kth direction velocity of the particular particle. And Fk is interaction force on particle in kth direction. Is this one clear? And rho d Vd into Gk is the body force. Okay. So do I need to consider any other force? Because we are writing this equation for a dispersed particle, and we make this assumption that dispersed particles are not crossing the boundary of the control volume, so there will not be any surface force at boundary of control volume on the dispersed particle. Okay. So this is my momentum equation for a single dispersed particle. And of course, the definition of total derivative is given over here, and we already know about this definition. Now, using this definition, on the left hand side, splitting has been done. Okay. So if I use this definition on the left hand side, I can segregate rho d Vd I am using as first term, and this I am using as second term, and then I am applying the chain rule using the definition of the total derivative. Is this one clear? Now if I do so, I will be getting that rho d into Vd, and inside it will be del by del t of ud k plus udi into del udk by del xi. Okay, and plus I will be getting some term udk times what I will get inside, del by del t of rho d Vd plus udk into del by del x of rho d Vd. What is that? From my previous number continuity equation, that term will become equal to nothing but id divided by n. Here nd is number of dispersed phase particle per unit control volume. Okay, is this point clear? So this you can refer to the continuity equation lecture. From there you will be finding the second term, whatever I will be getting in the bracket along with udk, that term will become equal to id divided by nd from my number continuity equation. Okay, then this will be equal to Fk plus rho d Vd into Gk. Okay, so this is nothing but the other variant of the continuity equation and momentum equation for particles, and this is also representing the effect of mass source term. Okay, so what does this term is representing now? As I told you earlier, whenever we write the momentum equation for nth phase, then what happens? Routine wise, our local and advective term will be there. In addition to that, if the size of the dispersed phase particle is either growing because of the phase change or it is decreasing because of the phase change or any other type of chemical reaction, then there will be additional change in momentum because of the mass exchange. So that additional change of momentum because of mass exchange is actually accounted for by this particular term. Is this point clear? Now, if I assume that in my system all the particles are of identical volume, okay, so identical shape and size. In that case, if Fk is the force acting on single particle, what will be the total force acting on all dispersed particles? That will be individual force multiplied by number of particles present in the control volume. Okay, so Nd is number of particle and force acting on individual particle is Fk. Is this point clear? All are clear up to this point? So if our assumption is, typically this happens if you have very well organized sample of solid particles. Okay, so sometimes you will be finding, for example, in handling grains and in handling say some granular materials in pharmaceutical industry. So there you find that the grains are of identical size and shape. Okay, so under these scenarios we can apply this type of equation. Now comes one important point. Let's try to understand that. Okay. So now question is, like, if I put a particle into the flow field, will it be coming in equilibrium with the surrounding phase immediately? Depending upon the size. Okay. So yeah, we can see that, say if I am having continuously flowing gas in the pipeline, and in this gas, if I drop some solid particles from the top, so initially when I am dropping the solid particle, then in the direction of gas, its velocity is 0. But whenever it has entered into this moving gas stream, it will be experiencing certain type of forces. And because of these forces, particularly the forces will be acting at the surface of this. Okay, and when these forces are acting at its surface, because of these forces it will try to change its trajectory. Okay, now once it is changing its trajectory, depending upon the unbalanced magnitude of the forces, either it will accelerate or deaccelerate. And when the forces acting on the particles becomes or comes in equilibrium, then after that particle will keep on moving with the same velocity without any acceleration. Is this one clear? So the time taken by a particle in order to adjust to the surrounding fluid situation, that is something which is called as relaxation time. Is this point clear? Why understanding of relaxation time is important? Because relaxation time will be giving us idea that how fast particle will be adjusting to the surrounding flow field. Okay, so if a particle is adjusting immediately to the surrounding flow field, then what will happen if we have any fluctuations present in the surrounding flow field, then particle will also quickly try to change its dynamics depending upon the surrounding. Okay, but in case the relaxation time or the time taken by particle to adjust to the surrounding fluid is more in comparison to the time scale at which fluctuations are happening in the momentum field or velocity field of surrounding phase, there what will be happening, particle will be lagging with reference to the changes in the fluid motion, and most of the time your particle will always remain in state of acceleration or deacceleration. Is this point clear? All are understanding this point? So how to determine what will be the relaxation time of the particle? In this case, what we do, typically if you see, when particle is accelerating or deaccelerating, then which force is coming into action? So inertia force is coming into action, which will try to resist the motion of the particle. And ultimately, why particle is actually moving? That is moving because of the interaction force coming from the surrounding fluid. Okay, so interaction force which will be coming on particle, if I assume a spherical particle, so on a spherical particle it will be majorly coming because of the drag force which is provided by particle of the surrounding fluid. Okay, so to determine the relaxation time of particle, how fast it is responding to the surrounding flow field, we have to balance inertia of the particle with the drag force acting on it. Is this point clear? Now what will be inertia of particle? Size of particle, so mass of particle into its acceleration. Okay, what will be acceleration? D square by dt square of its position. Okay, so say position vector is r. That will be its acceleration. Second derivative with total derivative in terms of position will be its, what will be its inertia force. Okay, and the drag force acting on the particle. So as I told you, if I consider the spherical particle, we know that drag force is of two types, form drag and skin friction drag. And on a spherical particle, drag force is given by Stokes solution, and as per that, drag force acting on the spherical particle is 6 pi mu c, where mu c will be density of surrounding dynamic viscosity of surrounding continuous phase, 6 pi mu c into r. Okay, now this d square r by dt square, because I am not balancing the equality sign, I am balancing it in terms of order of magnitude analysis. So if I am balancing it in terms of order of magnitude analysis, I can define that mp into, here say my length scale is r, and for time my time scale is t u. Okay, which is the relaxation time through which particle has accelerated or deaccelerated before coming in equilibrium with the surrounding fluid. Is this point clear? So here this I am using with tau u, and this will be equal to 6 pi mu c r, and now if you balance from here, you will be getting that tau mu is equal to 6 mp divided by 6 pi r into mu c. Is this point clear? Okay, I have made one mistake. I think this will be stress, and then multiply, one more r will come here. Okay, so one more r will come here, 6 pi mu into r square. Where? Yes, so when we will be calculating Stokes force, please make this correction. It will be 6 pi mu c r into u. U is velocity, and this velocity I can replace again with then r by t. Now it is coming. Is this point clear? So I have missed one velocity over here. Okay, so whenever we estimate the drag force on a spherical particle, that comes out to be 6 pi mu rc into u. Okay, and this u, which represents the relative velocity between the particle and the surrounding fluid, this u can be written in terms of order of magnitude of r by t. Okay, so ultimately r, or you can, if you want to use for position vector, then you can use even x. Okay, so this x will be cancelling out over here, and ultimately you will be getting t mu is equal to mp by 6 mu 6 pi r mu c. Is this one clear, or do I explain it again? See, it's very simple. mp into position vector is, say, x. So d square x by dt square. This is of the order of 6 pi mu c r into u. Now this u can be written in terms of 6 pi mu c r, and u can be written in terms of position vector by time, and this can be written in terms of position vector by time square. Okay, so from here different terms will be cancelling out, and ultimately I will be getting my relaxation time as mp divided by 6 pi r into. Is this point clear?
Still there will be r by t square.
R by? No, this t will be cancelling out over here. See, this t and this t.
So if this T cancels out, then how it will get T?
Here it is T square, na? This side it is T square and this side it is T. Yeah. So this particular thing is called as relaxation time. So it means that if I give you the mass of solid particle and if I tell that this particle is of spherical shape having radius r, and if I tell you that mu c is the viscosity of surrounding continuous phase, then you can tell me how much time particle will be taking in order to come in equilibrium with the surrounding phase. Okay, and from here you can see that this relaxation time is directly proportional to mass of the particle. So it means if mass of particle is more, its inertia will be more and it will be taking more time to come in equilibrium with the surrounding. Okay, and you can also see this time is inversely proportional with the size of the particle and the dynamic viscosity. Okay, so if fluid is more viscous, it will immediately try to impose the surface forces on that, which will balance with the inertia of the particle and bring it to the equilibrium position. But if viscosity is less, then the surface forces will be taking more time to come in equilibrium with the inertia forces and particle will be having high relaxation.
Is this equation like we had used relaxation time equal to your T by sorry. So here we have used similar sign like they are not equal exactly equal like inertia is similar to drag force.
That we are doing actually order of magnitude analysis. Yeah. Okay. So typically, have you seen this scaling analysis in your fluid mechanics?
Yes, like we have 5 to 50 then it should be taken as one like
No.
Derivation to boundary layer.
Yes. Whenever we derive the Prandtl's boundary layer equation. Okay. So there we do order of magnitude analysis, and then depending upon the order, if some terms are very less, then we neglect. Okay. Okay, now this is about the momentum relaxation time. After momentum, what else can happen? It can happen that your particle which we are dropping into the surrounding phase, that is actually hot or colder in comparison to the surrounding phase. Okay. So if particle is hot, of course it will be losing heat into the surrounding continuous phase, and if it is cool, then it will be gaining heat unless or until it is coming in equilibrium with the surrounding phase. Okay. So typically you can see I have given you one example that in fly ash what happens as particles are actually conveyed with the compressed gas. Okay, so if we see that with the high pressure gas, so if we see that if gas is coming at room temperature and particles which are coming from the furnace, these are having high temperature, then there will be some heat transfer also. Okay, similarly what we do typically whenever we do fire our these pulverized coal feed fired burners, so what we do there, burner is having some hot air which is mixing with the coal particles. This is preheating the coal particles and then finally these are burning in the furnace. Okay, so along with the momentum exchange between the particles and the surrounding continuous phase, there can be energy exchange also. Okay, so to understand energy exchange and the time scale at which this heat transfer will take place, we have to actually first understand our energy equation for multiphase flows. Okay, so typically we define specific total energy as, what is specific total energy in basic thermodynamics? Please tell me. Specific total energy is sum of specific internal energy, okay, plus kinetic energy which is given by half of ui into ui plus potential energy which is given by gz. Okay, why I am calling this specific? Because it is written on per unit mass basis. Then we define energy equation for a control volume in thermodynamics or for an open system. How we define? Del by del T of rho E star, which is rate of change of energy within the control volume, plus del by del Xi of rho E star into Ui, which is inflow and outflow of the energy across the boundaries of the control volume. Okay, but whenever I am writing this term like this, what it is representing? It is representing net outflow of energy from control volume. Is this point clear? Why I am calling it as net outflow? Because in a control volume, when some energy is entering, that energy can enter with any initial state. It can be E star 1. But when energy will be going out, because within the control volume energy content is E star, so outflow of the energy from the control volume should also be with the same energy content E star. Are you getting this point or not? Say this is my container. In this container, water is entering at 10 degrees Celsius. Okay, and inside this we are doing some heating, cooling or whatever thing, and this inside water is at 25 degrees Celsius, like in our geyser. Okay, so whenever I will be taking the water out from this outlet pipe, it will be at what temperature? It will be always at the temperature within the geyser, within this control volume. So say it will be at 25 degrees Celsius. So now if you have to write total change of energy across boundary, then you will be writing m dot inlet into energy corresponding to 10 degrees Celsius as inlet energy, and outlet energy as m dot o into energy content corresponding to 25 degree Celsius. And if I have to define the energy within the system, that will be also corresponding to 25 degrees Celsius. So it means that if I am writing over here rho ui, and with this if I am using E star, what it means? What is E star? Here E star is specific total energy within the control volume, and that specific total energy only I am writing when I am writing the energy exchange across the boundary. So it means that over here I am talking about net outflow of energy from the control, because outflowing energy will be having thermodynamic state E star, incoming energy can have state other than the E star. Point is clear? And then I will be having what can happen in a control volume. There can be heat interaction with the surroundings. Okay, so heat interaction with the surroundings is Q. There can be work interaction with the surroundings, that is W. Other than that, what happens when we have a moving fluid across the boundaries of control volume? Do you know something about flow work? In basic thermodynamics, we define one parameter as flow work. What is flow work? VdP, or in simple sense, it is nothing but pressure into velocity multiplied by mass flow rate. Okay, so mass flow rate into pressure into velocity. Is this point clear? So that is my flow work. Now here you see this term del by del xj of ui into sigma ij. Sigma ij, how I can write? Minus p del ij plus sigma c d ij. Is this point clear? All are clear with this idea? So when I will be doing this substitution of sigma ij, then this term del by del xj of ui into p, this term will give my flow work. All are clear with this point? And other than flow work, in thermodynamic analysis we do not consider, because in thermodynamics we say that we are dealing in the equilibrium conditions and ideal conditions. But if you go into actual scenario, then across the boundaries of the control volume there will be some what shear stresses, okay, and whatever the energy which we are applying to overcome these shear stresses and which is wasting in order to overcome the shear stresses, that energy is something which is called as viscous dissipation. Okay, so the second term, deviatoric part, whenever it will be multiplied with velocity, it will be giving me the viscous dissipation. All are clear with this point? So here you can see that this particular term is something which is accounting for both the things, flow work plus viscous dissipation. Is this point clear? So till now we have not introduced anything about multiphase flow. What I have done, I have given you the generalized form of energy equation just for the single phase flow. Okay, so whatever you study in thermodynamics, that energy equation is actually for area averaged quantities. Okay, and here I am defining this in differential form for a generic system. Is this point clear? Now, if I make assumption of steady flow, what will happen? First assumption is steady flow. What will happen? This first term will become 0, because what does it is representing? Time rate of change of energy within the control volume. Okay, steady flow situation is when property with the time is not actually changing. So for steady flow, first term will be 0. Then let me make the second assumption, no heat and work interactions. Q and W will be 0. Okay. Then third assumptions, negligible viscous dissipation. What will I get? What is the meaning of negligible viscous dissipation? When in this sigma ij, I will be replacing it with minus P delta ij plus sigma C dij, then the effect of sigma C dij will be equal to 0. Is this point clear? Because this is something which is a viscous stress tensor, and whenever it is multiplied with velocity, it is representing the dissipated energy content. Okay. So once I am writing negligible viscous dissipation, this sigma C content will be 0. But which term will be left? Minus of del by del x into P. All are clear with this idea? Okay. What I am having over here, you see, del by del xj and minus P into delta ij. Delta ij will be 1 only when I is equal to j. So what I can do, I can write this term as del by, because j is I, so del by del xi into P minus del P by del x. Is this one clear? Sorry, into ui will also come into picture. All are clear with this idea? Now what I have done, this is my left hand side. Okay, in the left hand side, I have taken this del by del x I p u I term to the left hand side. So if I take it to the left hand side, del by del x I, rho u I will be coming constant, and inside I will be having E star, okay, E star plus P, because this term is having one row outside the bracket. So, and with P there was no row, so one row has to come in the denominator. Is this point clear? So simple algebraic manipulation, whatever this simplified term I have got, I have taken it to the left hand side. Okay, so it has become del by del xi rho ui E star plus P by rho. What is E star plus P by rho? Can you tell me what is U plus P by rho? Enthalpy H. Okay, internal energy plus flow work is something which we call enthalpy. Okay, so this is enthalpy, and if I define H star as enthalpy plus half of ui plus gz, so this will be becoming total specific enthalpy. Okay, so I can replace this term E star plus P by rho with del by del xi of rho ui H star, and because I don't have any heat and work interaction, so right hand side will be 0. Is this point clear? So till now we are only talking about the energy equation in single phase flow. Clear? Now let us introduce the concept of multi-phase over here. Okay, so it is better to understand the energy equation first for single phase flow. Now you can correlate the terms for multi-phase flow. When I am writing this total specific energy for multi-phase flow, I have now added one additional subscript, and that additional subscript is N. Okay. Now when I will be writing with reference to the phase which we are considering. Okay. It can happen in a control volume that one particular phase is at T1 temperature, other phase is at T2 temperature. So internal energy of phase 1 will be different, phase 2 will be different. So that's why this energy content, specific energy content of a phase will be specific to a particular phase. All are clear with this? Even if these are at same temperature, then also their molecular structure is different, so they can store or they can have different type of internal energy. Is this point clear? So this is my En star. Now what will be the rate of change of energy? So rate of change of energy will be rho n into En star, but in the control volume, complete volume is not filled with the same phase. Only alpha n fraction is filled, so alpha n will also come in multiplication. Plus del by del xi of rho n En star into u and I into alpha. Okay, so this is representing the net outflow of energy across the boundaries of the control volume for a particular phase. Is this point clear? Now, only I have written the left hand side of energy equation for a phase. Okay. What about right hand side? In right hand side, I have Q, W, and this additional surface force term. Okay, flow work and viscous dissipation term. So, in the right hand side, when I will be talking about the multi-phase flow, particularly if I talk about one dispersed phase and one continuous phase, okay, then I will be having now multiple work interactions. Okay, so total work interaction for a continuous phase, what is this? This is total work interaction. Total work interaction for a continuous phase will be equal to work interaction, it will be equal to internal work interaction and plus this comes as external across boundaries of control volume. Okay. Now what do you mean by this internal work interaction? Can you give me some idea? Continuous phase, so dispersed phase will be applying some amount of force on the continuous phase, and while they are relatively moving with each other, there will be some work which is acting on continuous phase because of the presence of the surrounding dispersed phase. Is this point clear? Do you understand this point? If I have a dispersed particle present that dispersed particle will be providing some resistance force to the continuous phase, and if particle is remaining stationary or say moving at slow velocity with reference to continuous phase, then continuous phase has to take some deviation across the particle and move across its sides. Okay, so while this surrounding phase, continuous phase, is actually displacing across the surrounding phase, then it is investing some amount of work, and that work investment is coming as additional investment only because of the presence of that solid particle there. If that particle would not have been there, then that additional work should not have come. Is this point clear? So it means the way particles are exchanging the forces between each other. So ultimately, forces are just to make the balance, okay? But in order for the particle to move, there should be supply of energy. And supply of energy will be coming in terms of the work, okay? So particles are having some interaction forces with the continuous phase and also some motion. So the interaction force when multiplied with velocity, that will give me interaction work. Is this point clear? So this interaction work is actually internal, means within the control volume, this work interaction is actually done. Are you clear with this point? And other than that, continuous phase is also also sharing the boundaries of the control volume. So for example, this is a pipe. So in this pipe, when flow is happening, it has to overcome the friction. In order to allow the flow to happen, it has to supply some flow work. So that type of work interaction is actually accounted for here, which is external across the boundaries of the control. Is this point clear? All are clear with this idea? So for continuous phase, total work interaction will involve internal work interaction because of the interaction between the particle and the continuous phase, plus external which are acting at the boundaries of the control volume. When I will be talking about dispersed phase, what will be total work interaction for dispersed phase? Because dispersed phase is completely present within the control volume only, so it will be majorly having the forces in terms of the interaction forces with the surrounding. It will be having work only in terms of interaction work with the surrounding continuous phase. Is this point clear? Now comes this left hand side we have already seen. Okay, left hand side we have already seen. Then in right hand side it will be Qn. Okay, Qn is heat transfer with external surroundings. Okay, and one more term is there, Qin. What is the difference between Qn and Qin? Qin will be heat transfer with internal surrounding phases. Okay, what is the difference? Say this is my phase 1, this is phase 2, this is phase 3, this is phase 4. Okay, so what will happen? This is a complete control volume. So through these boundaries, this phase 1 is actually interacting with the surroundings. So in this portion, whatever heat transfer will be taking place, that will be my Q time. Is this point clear? But in this portion of phase 1, it is interacting with second phase. Here it is interacting with third phase. Here it is interacting with fourth phase. Okay. So the interaction in this portion will be with external surroundings, and these interactions will be with internal surrounding phases within the control volume. Okay. So heat which is transferring with this external boundary, that is my capital Qn, and the energy interaction between this and this, their total sum is actually summation of Qi. Is this point clear? Likewise, for work interaction also this will be valid. Wn will be the work interaction with this, and Win will be the work interaction between these particles. All are understanding this point? Okay. And then we will be having the additional work interaction with the boundaries of the control volume, and this additional work interaction will only come for which phase? Continuous phase, because our initial assumption was that all the dispersed phases are where? Not present at the boundary. Okay, at the boundary only we have present as continuous phase. So this will be only applicable for continuous phase. All are clear with this point or not? So this is what? This is my nth phase energy equation, or I can call it as individual phase energy equation. Okay. Now what is this? All of you understand this, or do I need to explain it again? Yes. If one is giving energy to 2, say x amount of energy, then for 1 x is loss minus term, but for 2 x is gain. If 3 is giving y amount of energy to 1, then for 1 y is gain, and for 3 y is minus. So likewise, whenever I will be doing summation of all the equations, all the phases, then this interaction term has to come equal to 0. Okay. Similarly, work interaction also has to be equal to 0. And epsilon n is some other form of energy interaction. So say other than heat or work, if any other energy interaction is happening between the phases, any other form of energy interaction that is not accounted for now, but maybe in the further equations it may be there. So summation of that other form of internal energy interactions between the phases will also be equal to. Okay. Last is any energy, class. You can go. Okay. So I will stop at this point only, and then we'll discuss further.